Friends, Pythonistas, and Djangonauts, lend me your brains and let me add a mental model, an insight about programming called data-oriented design and how we can apply it to Django. Computers are friggin' fast, okay? They're friggin' fast. It's something you have to realize. This laptop here, each core can do 3.2 billion operations per second. And it has 10 cores, 32 billion operations per second total. I tried to compare with Grug-brained Adam. This computer is 64-bit. I generated 2 random 64-bit numbers and tried to add them together. That counts as one operation. It took me 55 seconds. I came up with this, and it was the wrong answer. One of the 6's should be a 5. So if we compare the computer with me at maths, I can do 0.018 operations per second at 0% accuracy, and the computer can do 32 billion operations per second at 100% accuracy. Where does all that speed go? My Django view, I think it's doing hundreds of things, and yet it should be instant, and it's taking seconds. What's happening? This is what data-oriented design tries to address. But first, what is not data-oriented design? It's not domain-driven design, which we heard about earlier, and may not be a piece of crap, I don't know. It's not data-driven design, which is a term I've heard for building layered architectures. And it's not data-oriented programming. Just to confuse you, there's a book out there. That's a kind of adjacent term, but it's not exactly that. So what is data-oriented design? First, we need to adopt Shoshin, the Zen Buddhism term for beginner's mind. Beginner's mind tells you that in any line of inquiry, you should try and empty your mind as if you're a beginner, no matter how much you think you know already. So, let us return to my high school computing class. I was shown this diagram, probably in the first lesson. What is software? Software takes input data, it runs on some hardware to transform that input data, and turns it into output data. That's data-oriented design. Thank you. That's the insight. Software's only job is to transform data. Anything that we add to software, any kind of thinking about architectures, do I use this technology or that? It's all in honor of this one goal, and it's all secondary to this goal. Users of your software only care about getting that output data, and in a timely fashion, accurately, whatever they care about that output data, but they only care about getting it. And whatever you do in the middle, as long as it gets the output data, it's kind of okay. It's kind of fine. So that leads us to ask, what are the characteristics of the data that we're transforming? And every single problem is slightly different. The data may be in different formats. It may come at a different volume. It may be loads and loads of data at once, or maybe a tiny amount. It may come with different latency characteristics. Your input data might be coming sporadically or in very many chunks very quickly, and then users will only care about their output data with a certain latency as well. And that gives you your throughput. And then we can also ask questions about what is the statistical distribution of the data, because that can influence the way we program. Context is everything. If you have different input data and different hardware, that should lead you to build a different algorithm to get different output data. Let's look at an example, so you can maybe see a bit about what I'm talking about. Say you've been given the problem to check if a number exists in a given set of numbers. Perhaps your Python brain is already going, oh, you can use the in operator with a set. So you might come up with this function. There's some set of numbers that's stored already, and then we implement our function, is this number a match? We just say, return number in numbers. Seems pretty reasonable. What if there was just a single number in that set? building a set would be to contain a single number, and using the in operator would be slightly wasteful. So we could just use the double equals operator. What if the set of numbers we're checking against is 1 billion? Putting 1 billion numbers in memory in a Python set is probably going to exhaust the memory, maybe even on this computer. So that's probably not a good idea. So you might end up putting them in a database. SQLite would be fairly reasonable. So you could do it like this. What, though, if we were matching many numbers against a few? Many functions in our programs aren't called just once. They're called repeatedly with the data that we're matching against. So it might be more reasonable to write our function to take in a whole set of numbers to match at once, and then do that more efficiently. So in Python, you could use the intersection operator. We can take in a set of numbers to search for against another set. Well, that's also built into the set class for us. We could go on. What if the set is all numbers, all odd numbers between 1 and 1 million? Well, we could write just a bit of maths instead of storing all the numbers. What if false positives were acceptable? In that case, a Bloom filter might be a better data structure. Bloom filters are cool. I don't have time to talk about them here, but do look them up. And so on and so forth. But the important thing here is that the data that we're using as inputs to our function will influence what function we write, and also the context, because if this function is maybe being called in a loop and we can do it efficiently in one pass, that's also better. Yeah, so the implementation that we come up with depends on the characteristics of the data we're working with. That is data-oriented design. The other side to it is that the job of software is to transform data, but only using specific hardware. When we write a program, we're only going to run that on certain computers. The world of computing is infinite. We're targeting rather specific computers whenever we write a program. That makes us ask, okay, what is the hardware we're writing for? Are we writing our code to run on a TI-85 calculator? Probably not, at least not in this room very often. Are we writing something to run on a quantum computer? Probably not here. What about the Turing Tumble? This is a marble-based computer. It's a huge amount of fun. But probably not. It only supports 4-bit numbers. Most of the time, everyone in this room is writing software to be running on the general-purpose CPUs of the day. That's what's in my laptop. That's what's in servers that I deploy to. That's what's in my phone. There's other chips in there as well. But our Python code, our Django stuff, is mostly running on general-purpose CPUs. Well, that leads us to ask, what are the characteristics of modern general-purpose CPUs? Here's a picture. There you go. All of our CPUs are built on something called the von Neumann architecture, which is basically the CPU executes instructions one at a time. It fetches the instruction and potentially data from memory, runs the instruction, and maybe writes something back to memory, depending on the instruction. So far, so good. But this diagram is a vast oversimplification. This is the history of general-purpose CPUs since 1980. If we peg the relative performance of the processor and the memory transfer at 1 in 1980, fast forward to the modern day, and there's a gap of around 1,000-fold difference in speeds. So your processor can do a heck of a lot, but it can't get the stuff from memory. This is a diagram I got from a book. Whose name I forget, but it will be on the blog post. So, CPU manufacturers introduced a cache between the CPU and the memory. So the data is transferred into the cache, which is way faster, but way smaller. So the working data can be fetched and stored from the CPU rather quickly, and then when it needs to make its way back to memory, it does, but hopefully that's less often than it's used, because most programs, they focus on a small amount of data at a time, and then they are done with it. That is a vast oversimplification. The modern CPUs have 3 levels of cache, sometimes 4. Each layer of cache is about 3 times faster than the next one, but about 3 times smaller, give or take. So when you're running something on your computer, and you're writing your Django view with levels of caching, and you're thinking, oh, this is a bit hard. Your computer's doing it way harder. So for this computer, I looked at the stats. I think these are about right. A fetch from the level 1 cache takes 3 cycles. That's 3 of those operations per second. But going to the level 2 cache takes 10 cycles. Going to the level 3 cache takes 30 cycles. And then going to memory takes at least 100 cycles. We have to work with this reality. This is the hardware we're writing for. What are the implications of this then? Well, put simply, use smaller representations. The smaller it is, the more of it you can fit into that bottom level cache, and the faster you can go. And then the second implication is to lay out the data in access order. One extra thing the cache is doing is it's prefetching data. So you access one piece of memory, it assumes you'll access the next one. So if you're going through memory in a line, it's actually going to be almost as fast as going through cache all the time. That leads us to ask about Python. Here's just a quick example of how Python is kind of wasteful. This is a 64-bit computer, so we divide that by 8. That's how many bytes there are in a full-width integer. But if we import Python's sys module, we can use sys.getSizeOf to return the size in bytes of, here, the number 9001. So that's an integer 9001, and it's 28 bytes. What's going on here is that Python has the number, but it also has 20 bytes of other stuff about the number. So it has an object ID. Everything in Python is an object. So the overhead here, it's nearly 4 times the size of the actual number. That's the reality. If we build a list of numbers in Python, and we say, okay, there's 1,000 numbers here, multiply that by 8, that's how many bytes of memory it should take up. It's 8,000 bytes. But if we add together the size of the list, which is the container, and then the size of all the numbers within it, it's 36,052 bytes. So again, it's about 4 times the size, bit of wastage. But Python has a solution. You can build this object called an array that packs all the numbers together and treats it as one line of memory. And if we build an array of the first 1,000 numbers, then we end up with 8,320 bytes. There's a little bit of overhead, but it's nowhere near as much. So it's a bit more reasonable. That said, the array type isn't that useful because it doesn't have many operations. So if you are using arrays of numerical data, much better to use NumPy or Pandas, which do the same kind of packed format, but they also have a lot of routines for transforming the data in an efficient manner. Okay. So now we can ask about applying the data-oriented design model to the web. What is the input data, the output data, how are we going to work with it? Here's my approximate diagram of any website ever. We've got the user, and they send clicks, or indeed any other interaction, like keyboards, or perhaps they're using voice control, to the browser. The browser sends requests to our something, which we'll define later. And then we need a database, because users of most websites expect their data to stay around in between interactions. And then it goes back from the database through something and needs to be transformed into HTML for the browser. And then the browser turns the HTML into pixels on the screen, and the loop can continue. Note that we're sending HTML to the browser. That's the only thing that browsers accept for rendering stuff on the screen, minus a few small JavaScript APIs where you can directly put pixels on the screen. But 99.9% of the time, we're using HTML to tell the browser what to render. It's up to us as web developers to choose what to put in that something cloud. Just like to note, I'm not going to put the user-browser interaction here. We don't have control of this loop, and it's also already hella fast. Like browser super optimized, written in C and Rust and whatever, and a well-run web page, there's no noticeable lag for the user. So I'm going to skip that on the future diagrams. So yeah, we're just going to look at this. What are we going to put in the something? Well, one option is to put Django in the middle and then use Postgres as our database. So the browser sends a request to Django. Django turns that into one or more queries to the database, getting results in order to construct HTML, give it to the browser. Job done. You could also build an architecture like this, which is not unrealistic in the modern era. Your first request, you send a bundle of JavaScript to the browser. Then the JavaScript, which we could think of as a program separate to the browser, just running in a sandbox, makes some more requests to an API gateway. The API gateway forwards the requests to service 1, 2, or 3, each of which has their own database. A lot of work going on in order to get the gateway back, and then the JavaScript eventually constructs all the results and turns it into HTML. Bit of a mouthful. One question. How fast does our data transfer need to be? How fast do we need to get the HTML to the browser? This is the key data characteristic for performance. If we can do it in less than 100 milliseconds, you get a double OK sign. Very good. Less than 1 second. That's pretty good. Oh yeah, I put 100 milliseconds because that's the threshold of perception. So if you can update the screen in less than 100 milliseconds, it'll feel instant to the user. Anything around that as well is pretty good. If you get to about 3 seconds, I saw something that, you'll lose 50% of visitors on mobile devices who are doing a first page load if it takes more than 3 seconds. So you're already a bit on the edge there. If you get past 10 seconds, I'm sure you've tried to load a web page, waited 10 seconds, and you just close the tab, you hit refresh, or you're gone. So that's our kind of limit here. It's not much, actually. Still, if we're using like C and stuff, you've still got a lot of network interactions between you and the browser, so that doesn't leave much time for perfect experience. All right, we're going to go look at the two sides of the diagram now. We're going to first dive into how we can improve the flow from request to Django and then Django to HTML back to the browser. Speeding up the request response cycle. There's quite a lot on this topic, and so I've just put a few bullet points on this slide, and I'll refer you to other resources. The first thing we can do is write minimal performant HTML. There are good ways to write HTML. If you get your style tags and your first JavaScript tags in the first kilobyte, the browser will start requesting those early on, even whilst it's downloading the other HTML. Don't bloat your HTML with loads and loads of classes that some CSS frameworks like to add, etc. Introduce HTTP caching. You can tell the browser which things it can fetch once and then store forever, so you can have your images loaded once only. Very good to add. Get onto the latest version of HTTP. There's HTTP 3 now, and there's HTTP 2 way more widely available. Make sure you're using at least the HTTP 2. Look into response compression. Django has gzip middleware built in, which will gzip your requests. That's a compression algorithm. For text formats like HTML, you'll see like pretty good savings. There's also an alternative called Brotli that's available only on HTTP2, or is it only on HTTPS? One of them. Django doesn't have built-in support for that, but it could grow that. It's slightly better than gzip. You can also look at HTML modification. This is when you're really trying to save the bytes. I found a Rust-based HTML minifier that it will save you about 1 to 3% of your request size. Still something, and I made a middleware in the package Django Minify HTML. And I think maybe the most important is to deliver with a CDN, because if you're putting your content through a content delivery network, that's a bunch of servers around the world, and the data for your website will go to and from their servers, which are closer to users, saving a lot of the network time. That's the primary time that we can affect on this request response cycle. I'm going to refer you to some resources here. If you look at MDN, the Mozilla Developer Network, they've got a page called Web Performance. That's a very good section in the docs. Google Chrome team have web.dev, and so there's webdev learn, and then I've got two measurement tools. One is webdev measure, and one is web page test. You can run either of these tools for free on your website, and you can see what's taking time in the request response cycle, what is the browser having to do from what you've told it in your HTML, how long a connection's taking. You can time them from other side of the world, etc. So you can really dig in and optimize that part of the flow. All right, time to look at the other side, somewhere where our advice gets a little bit more specific to Django. We're making queries to Postgres, and Postgres is returning us results. And we're probably doing that a number of times for every HTTP request we get in, because we have to assemble different pieces of data on the page. So yeah, that's what we're looking at speeding up. Returning to the CPU memory diagram, you might remember it took 100 cycles to get something from memory. Well, unfortunately, the story is pretty bad when talking to a database over a network. It's going to take 1.6 million cycles, at least, to get there. This is assuming a half a millisecond round-trip time to Postgres and pretty much an instant query. If the query starts taking a few milliseconds, this will go up by a factor of 10, you know. So that's kind of the answer to the question, where does all the speed go? And anything we can do to reduce the number of times we do this trip, kind of the better. So let's look at 3 ways to speed up queries and results. The first one, avoiding the n+1 query problem. This is a classic. I'm going to dig into it. The second one is to look at splitting your models into smaller logical units. So both less data is fetched over the network, less data is moved around in memory, and less data is also in each individual table in Postgres, so it has to do less work to look through your tables. And then I'll show you kind of a slightly more advanced technique about how you can batch counts into one pass. I hope this set of things is very small to cover on database optimization, but I hope it inspires you to go look at some other things that I'll point you to. All right, what is the n+1 query problem? Who's encountered the n+1 query problem? Okay, so reasonable amount of experience. I'll go over it again. Hopefully you learn a little bit of something. Look at this code. It's looking at some books, and then it's printing them out by the book name and the name of the author. How many queries does this do? It does n+1, if you might have guessed that. The first query comes when we iterate the books query set. That turns into a select query for give me all the books database, and it gets them in one query. And then within our loop, for each of them, when we touch the property, the attribute book.author, the Django goes, oh, I don't have the author, I didn't fetch that. I'll go fetch it for you. But it does that on every single iteration of the loop. How can we fix this? Here's one tool. It's called select related. So here we do a single query, and we ask for the database, give me all the books, along with all the author data. What happens here? We get a single query where all the book data and author data is joined in. When receiving that data, Django splits it up again into in-memory model objects. So all of the data for the books goes into the individual book objects. All the data for the authors goes into separate author objects that are linked. So we've done it. n+1 queries has become one query. This will go way faster. We avoid that back and forth to the database many times. There's a little bit of a drawback to select related, and this table hopefully demonstrates that. SQL databases only talk in tables. So when you do a select-related query, it's coming back as a single table of data. We've got all our books, and I've put their names down the left column here. There'll be other columns. And then we've got all of our authors joined in, and they're on the right-hand side. I've put only the name column as well, but you can imagine there'll be other columns. The problem we've got here is extreme repetition, because one author was incredibly prolific. Imagine if we had way more rows. Arthur Conan Doyle is appearing many, many times in the data set. At some point, that volume of data from passing over the authors repeatedly, the same author over and over again, is going to outweigh the savings of using select related. It kind of depends on your data, but you do need to think about it, measure. For this, Django provides, to solve this problem, Django provides a different tool called Prefetch related. Prefetch related says, when you do this query, also prefetch and do a second query. So we'll get two queries out of this. The first query fetches the books when we start iterating on them, and then as soon as Django's done that fetch, it sees that there's also a prefetch to do, and so it looks through the list of books and it fetches the authors for the books it fetched. So if there were 5 authors for 1,000 books, it's going to do a query that pulls back just the 5 authors once. No repetition in the transferred data. This can be faster than using select related. It does depend, as I say, on the data volumes. You have to do a bit of measurement or guessing. I think prefetch related is generally a better default to reach for than select related, because yes, it does one extra query, but it's limited still. It's going to be 2 instead of n. With that, I'd like to talk to you a little bit about a project I've been maintaining for a while that my old boss wrote called Django Auto Prefetch. If you swap your models and query sets to the versions provided by Django Auto Prefetch, it has like a slight patch in the ORM to change Django's behavior. So remember that the n+1 problem was caused by us touching the book.author attribute and Django fetching one of them. Django Auto Prefetch changes this logic and says, I see you access the author of a single book, but that book was fetched as a larger group, as part of a larger group. I imagine you're going to do it again on the second iteration of this loop, probably. So it just fetches the authors for all the books in one prefetch. So we end up automatically with the 2 queries done rather than n. So Django Auto Prefetch, useful project. It solves your n+1 query problems for foreign keys and one-to-one fields. It doesn't help you with many-to-manys where you're doing a new whole query set within the loop. I don't know if there's a way to do that. But yeah, check it out. Yep. All right. Second technique for reducing your data volumes to make things more performant is splitting models. Imagine we have a user model. It's inheriting from Django's abstract user, so it's pulling in a bunch of fields like username, email, password, and we've also got our own custom fields here, like the user's avatar. And then we're given the task. We need to store users' Acme access tokens and refresh tokens. We're talking to the Acme API, and we're going to get access tokens and refresh tokens from their OAuth thing. We need to store them so we can keep making requests. What you might feel like doing is adding a few fields on user. These are the Acme things for the user, so they should go on user, right? This is not great. And the problem is that it's going to slow down every place where users are queried. Every single query set of a user is going to automatically be fetching those fields from now on. Django's going to have to do work to deserialize them. They're going to take up space inside Postgres next to all our other data. One thing you might not realize about Postgres, every time you update a row, it's creating a whole new copy. So everything you add in a single row is having to do a copy of that data every time. So what's an alternative here? Well, we can make a second model. We can just create a model called the user Acme token, related one-to-one with the user model. And on that, we'll just put the 3 fields we need. and we'll use the user as the primary key for this model. So every user Acme token is related to exactly one user. And if we don't have Acme tokens for a given user, that model is simply not going to exist for that user. So we can still determine that easily. This is much better. It gets 3 thumbs up. All right. Now on to the third, slightly more advanced technique. We can do multiple counts in a single pass. Have you ever written code, maybe for a dashboard like this, where you want to show, say, the count of verified books for an author? I called it published in a variable. And the unverified count as well. So maybe 2 big numbers on the dashboard. These are doing 2 separate queries right now. Instead, what we can do is use a little bit more advanced feature in the ORM and send a single query to the database that asks it to count both parts at the same time. And what Postgres is likely to do here is make a single pass over the data, counting each kind separately on the way. So this saves a whole round trip to the database, it saves a whole pass over the data, and if an author had many books, we might see a fairly reasonable performance improvement here. So I included this as a slightly more advanced technique that you might not be aware of, which is this filter argument on all aggregates. You can do this not just with count, but with sum and average, etc. We have some fantastic resources for optimizing your use of the database, and it's a key thing in data-oriented design. Limit the amount of data you're touching. The first is in the documentation. There's this page, Database Access Optimization. It's a litany of all the things you can do inside Django to improve your queries. Everyone should have a reader list until they know every single part of it. I'd also refer to this book, The Temple of Django Database Performance. This is a very good first pass over things like indexes and joins and what the database is doing and features that you can take advantage of. And it's Postgres specific, but you might find most of the things apply to other databases as well. If you want to look a bit more at the N+1 queries problem, I wrote a blog post a few years ago, sponsored by Scout APM. Just search for that and you'll find it. And then it's very important for us to see the queries that are actually happening in our code as we're using it. So I'd recommend you use a tool like Django Debug Toolbar, which is universal, or indeed our sponsors, Colo, if you use VS Code. So, data-oriented design. Remember, software's only job is to transform data. And users only care about getting their output data in a timely manner. Here are some resources where I learned about data-oriented design. It's a term that's come out of games programming, where every cycle counts, and rearranging things in memory really helps. I think the original talk I could find was by this person, Mike Acton, who now works on the Unity game engine. And he gave this talk, Data-Oriented Design and C++. It says C++, it's not so C++ focused, I think. The thing that got me onto this term was Andrew Kelly, who's creating a new programming language called Zig. And his talk, Practical Data-Oriented Design, shows how he applied it inside the Zig compiler for some great speedups. And then this final talk here, Andreas Fredriksson, talking about context is everything. This is a very good optimization talk. He wrote something that parses JSON in C++ and then continually optimized it. At the start, it could parse the JSON and get the output answer at a rate of about 40 megabytes per second, which is quite a lot of speed for a single call. But as he changed it to use a specialized JSON parser and so on, he managed to get a single core speed of about 1,250 megabytes per second, like a 30 times speed up, way faster than anything we could ever write in Python. But yeah, very impressive. Computers are friggin' fast. All right, thank you. I've been Adam.